We're going to talk about the work-energy theorem, which relates energy and work, as the name implies. So the work-energy theorem, in order to talk about that, first we need to remember that Newton's second law relates net force and acceleration. That will become very important here shortly. So if we combine this with the definition of work, that work equals a force parallel times a change in x, well then what we can say here is that work is equal to the, if we assume that the net force is that force parallel, we have work equals m times a times delta x. And if we remember that v squared equals v naught squared plus 2a delta x, we can solve that for a and get v squared minus v naught squared all over 2 delta x is equal to a. Plug that in back over here. Work equals mass times v squared minus v naught squared over 2 delta x times delta x. The delta x's will cancel. And with a little bit of tiny rearrangement here, we get work equals 1/2 m v squared minus v naught squared, which equals 1/2 m times delta v squared. Which, in other words, the work-energy theorem, the statement of work-energy theorem is work equals force parallel times delta x is equal to 1/2 m delta v squared. So that right there is our work-energy theorem, that the work is equal to the change in kinetic energy here. The main reason we care about this is that it justifies that work will produce a change in the energy of a system. We see specifically it's creating a change in the kinetic energy, and that lets us then tie to a bunch of other things. In later units, we'll show the same idea for potential energies, but for now you can see how, and it makes sense, if you push on something, you can make it speed up, or if you push on something, you can make it slow down. You can add or remove energy by pushing on something for a certain amount of time.